Hello, this video will cover section 3.2, logarithmic functions and their graphs. The objectives for today's section will be to recognize and evaluate logarithmic functions with base A. Also to graph logarithmic functions, to recognize, evaluate, and graph natural logarithmic functions, and also to use logarithmic functions to model and solve real-life problems. Just so you get an idea why we're studying logarithmic functions in this section is because they are the inverse functions to the exponential functions that we studied on the previous section. So, we have here the definition of a logarithmic function with a base A. And I want to remind you how when we went over the exponential functions, we also had something that we referred to as base. And so we had something such as f of x is equal to a to the power x. And so the number that is being raised to a certain power, that is our base. And then we had here our independent variable, which is x, and is also, of course, the exponent. So when we talk about logarithmic functions, we will also use the term base. And in this case, the base has to be also greater than 0, just like we had that for our base here. We said it had to be greater than 0, and also it couldn't equal 1 because then we wouldn't have an exponential function. We will have a constant function. So it's same restrictions for the base of a logarithmic function, and it has to be greater than 0. It cannot equal to 1. Now, the base of a logarithmic function is going to be located here. I'm going to highlight it, and then I'm going to teach you how you will read expressions such as this one. So that is the base. We have it here as well. Right here, it looks like a little subscript for the prefix of log, of a logarithm, the abbreviation, not the prefix. So that is the base. Everything that I highlighted with pink is referring to the base. So the base will determine the type of logarithm that you are using. So we could have a logarithm with, and here we have this definition, just to generalize that a could be any number as long as it's not 1 and it's positive greater than 0. So we could have something that says log base 5 of x, and that is exactly how we will read it. Of course, there are other options. Log base 5 of x, or we could also refer to it as log of x base 5. And so that little number, it could be a 10, it could be a 2, it could be a 1/2, as long as it's greater than 0 and not equal to 1. Now, there are some special ones that we're going to use more, and those will be base 10 and base e, like the natural number, the one that we introduced in section 3.1. So those will have special abbreviations, or for example, I'll just tell you now, if we have something that is base 10, and we will actually just skip writing the 10. And so when we don't see a base, then it will be right away assumed to be of base 10. But we will go over that in a minute. So right now, the most important thing is for us to see the connection between both logarithmic functions and exponential functions. And so I did say that they are inverses of each other. We will see that with a graph as well. But also I want to say that we need to learn both, because being inverses of each other, they undo each other. So if we are solving an equation that has an exponential function, we will require some logarithmic properties to solve it, or vice versa. If we're solving a logarithmic equation, we will require some exponential properties to solve it. So they go hand in hand. They're kind of like multiplication and division, or addition and subtraction, or squaring something and taking the square root of something. So that's why we learn both of them. And so one of the first things that you should learn is how to convert from one to the other. But we will do that in a minute. And I want to make a little emphasis here of the statement if and only if. So we're saying that y equals log of x base a. We refer to x as the argument, and the argument is what you're taking the log of. So log of x base a, if and only if x, now we have the argument here, and then we have a, x equals a to the power y. And so that's one of the things we're going to learn also today, how to convert from one to the other, and then, of course, the other way as well. So the next thing we will do first, before we get to that, let's see if we could understand what a logarithm is. And so what we're going to do here is to evaluate logarithms. And so of course, we will use the same thing that was on the previous slide. You see how y will be here, the output for the logarithmic expression, but here is the exponent. And then we have the base, which is a, is also the base for the exponential quantity. And then x, which is the argument of the logarithm, is the output for a to the power y. All right, so let's, whenever you see evaluate, you need to find some sort of numerical value or expression after, performing some operation. So here we're going to substitute x with a 32, and then we're going to see if we could change it to, and I'm going to do the following. Well, actually, let's do this. So f of 32, you see f of x. It is a function, by the way. We will look at the graph. And this will be log of base 2 of 32. Notice how the 2 is smaller. It looks like a subscript. So how could we do this? So what we're going to do is change it to exponential form. So the way to change it, by the way, the double arrow implies the if and only if, which has the abbreviation IFF. And we're going to do the following. So first, I'm going to change f of 32. I'm going to just change it to the letter y. And then I'm going to take this y, and that will be the exponent of my exponential. But what I found to be the easiest way is to always start with the base. In this case, the base is 2. So this will be 2 to the power y is equal, and then what else is left for us to do? Well, the 32, the argument. So now, or if we wanted to look exactly that way, I can write it this way. I can write the 32 first, and then the base 2 to the power y. So now the question is, to what value would I have to raise the power 2 to equal, no, to what power should I have to raise the base 2 so that I get 32? And so that will be 2 times 2, that's 4, another 2, that's 8, another 2, that's 16, another 2, that's 32. So the answer to this will be y equals, we want 2 to the power 5. So something like this. The only way we could have make the statement true, it will be if we make y a 5. So the answer to the question, what is y, or what is f of 32, will be the number 5. That's how we will evaluate them, by converting them to an exponential equation. So we could also think of it like if we didn't have this side and we just had this expression here, we could think of it this way. To what power do I need to raise 2 so that I get 32? And the answer is what we had here, 5. Okay, so let's try to do another one by converting to exponential form. And so the very next one, we're going to have y, remember I'm just replacing f of x with y, is equal to log base 3 of, and now we're substituting x with the number 1. Okay, now we're going to change this to exponential. So we will have, remember we always start with the base, so in this case it's 3 to the power y. So you see I kind of like 3 and 1 look like 3 might be the base and 1 might be the exponent of 3. So think about it like switching them. So the 1 goes to this side and the y becomes the exponent of 3. So I'm going to put the y there. And then the number, what was that? Number 1. Number 1 is the argument. So that will go here, and here the exponent is y. So think about it. What number will y have to be so that this statement is true? 3 to what power gives you 1? And so the answer for that will be 0, right? Any number except for 0 to the power 0 is equal to 1. And so the answer to this question will be 0. That is the answer. So that's what we're evaluating. Okay, next question. So we'll replace this with a y, and we'll have log base 4 of 2. So let's convert it to exponential. So we start with the base, which is 4 to the power here, y. And that is going to equal to this argument, 2. So now, question is, to what power do we have to raise 4 to get a 2? And if it was the other way around, it will be easy, right? 2 squared gives you 4. But it's 4 to what power will give you 2? So I want you to think about a square root. So if we had something like the square root of 4, that will equal to 2. So how can we represent a square root with exponents? And the answer is this way, with fractions. So the index of the root, which with the square root is implied, we don't write it, but we know it's a 2. We don't call it the first root, it's the square root. So that number 2 is the index, and that will be the denominator of your exponent. So the exponent will be 1 over 2. So a half for an exponent represents the square root. And so the answer to this, the evaluation to this logarithmic expression here by substituting 2 for the x will be 1/2. Why? Because that will have to be the exponent that we will raise the base for to get a 2. Okay, next one. Now here we have the base 10. So the 10 is there, but it's not really required to be there. But here we have it. So we have log 10, log base 10, I should say, of x. And here we're going to replace x with 1 over 100. Okay, so that will be the argument, and 10 is the base. And here y is going to be the exponent. Okay, so we convert this to exponential, and it will be 10 to, I'm actually just going to put it on the right. It's not like a big deal, but I don't want you guys to get confused. Well, let's just do it this way. 10 to the power y is equal to 1 over 100. So to what power do we need to raise y so that we get 1 over 100? Now this one's a little tricky because our answer is going to be negative. And I say negative because 100 is clearly a power of 10, but it's the reciprocal of 100, so it's actually 1 over 100. So then I'm going to change 100 with 10 squared. But as you can see, it's still in the denominator. So now if I want to bring that 10 up to the numerator, the exponent of 2 is going to change to a negative 2. So this fraction will be 10 to the power negative 2. And now you could see clearly by the one-to-one property that we learned on the previous section, we know 10 is equal to 10, so then y must be negative 2. And so that is the answer here, the evaluation of that logarithm, negative 2. So now we're going to go over 4 of the properties to evaluate logarithms. And so here we're starting with what I was mentioning about the base 10. And so base 10 is called the common logarithmic function, and it is log to the base 10. On your calculator, it will just say log. So if you have your calculator around, look for that key. And you could see that for most calculators, you will see the key log. And then you will have a 10 to the power x on top as your second function. Other calculators may have the key of 10 to the power x, and then with a different color, they will say log. So these properties are very useful, and they are just generalized to base A. Remember, base needs to be A must be positive, greater than 0, and also A cannot equal to 1. So when we go over these properties, please know that they also apply to the common logarithmic function, which is base 10. So we have the first one that says that the log of 1 of any base will always be equal to 0. And that is so true because, as you saw earlier, if we take the base from here and we want to write it, here's the argument 1, and here's our log value. So we want to rewrite it, it will be A, and this is what I was saying about like switching the A now has the exponent 0. Not that the 1 was the exponent, but it kind of looks like it, and then the 1 just goes on the other side, as you could see here. So we know that any number, as long as that number is not 0, so as long as A does not equal 0, A to the power 0 is equal to 1, right? And we know A doesn't equal 0 because we made that restriction here. We said A cannot equal 1, but we also said that it needed to be greater than 0. We don't have the equal part of the inequality symbol there. So then this statement holds, meaning that it will be true for all A as long as they satisfy the property greater than 0, not equal to 1. Okay, next one. This is my favorite because you could just like literally make things disappear. So if you are taking the log of a number, here in this case A is the number, and the base happens to match that number, then the answer to that will be the exponent of the argument. And if we don't see an exponent, we know it's a 1. So it's like you cross this out, it cancels each other out as long as they are of the same base. If the argument and the base are the same number, and then you just take whatever is the exponent of that base. Since we don't have one, we know it's a 1. Now, if we convert that to an exponential expression, it will be A to the power 1 equals A. And we know this is true. Okay, property number 3 is the same as 2, but here now we do have an exponent. So we see the base matches the argument. So then the answer to this will be whatever is left as the exponent of the expression. So right here, that x, that will be the answer. So I also like to think of it like if they do cancel each other out, because I mean, after all, they are inverses of each other. And if we were to turn this into an exponential equation, it would be something like A to the power x, or A to what power? Let's just put like an empty box here. A to what power will give me A to the x. And so that will have to be x. So that's another way to look at it. Similarly, we have this other property that works in the same way. So if you have a base right here, base for exponential. And your exponent happens to be a logarithmic expression where the base of the logarithm matches the base of the exponential expression. So we could also cancel this out, and what we have left as our answer will be the argument, which will be x. And so those properties are very useful. Make sure you do learn them, make sure you write them down, and then make sure you refer to them when you're doing your homework. Property 4 is another of the one-to-one properties. And so that states that if you have two logarithmic expressions, and you're saying that they're equal to each other, then as long as they have the same base, they must have the same base, then you could say that the arguments are equal. So kind of like what we have here, we could say, if I was to make this, I don't know, a 2, then I could say 2 equals x, right? If the base is the same, a is equal to a, so then the exponents must be equal. So then with the logarithmic expression, we have log of x base a is equal to log of y base a. So since the bases are equal, the arguments must be equal. And this is also known as the one-to-one property. And number 3, they're known as the inverse properties. So let's move on to our next example. And for this one, we're going to be graphing both the exponential function f of x 2 to the power x, and the inverse function, which will be g of x equals log of x base 2. So what I want you to do is to create a table for function g, and since we already know, I told you they're inverses of each other. These are the x values, these are the y values, or we could say that these are part of the set of the domain. Or the input or the output. And so what happens when you graph the inverse function of it, they are going to interchange. So what I want you to do on the new table is to write the x values where the y values should be at. So let me make myself clear with colors. So we want those values for x to become the y values. So I want you to write that down. And that is only because these two functions are inverses of each other. So that's why we can do that. All right, now we are going to take the numbers that were here, the outputs for the exponential function, and now they're going to become the inputs for our logarithmic function. So we will have the 1/4, the 1/2, the 1, the 2, the 4, and the 8. So we interchange x and y. That is exactly what we did. That was studied back in, I believe, 1.9, in case you need to review. So the points that we will be plotting, of course, let's do the following. So I'm going to graph each function with a different color. So we will have the point -2, 1/4. This is just like a horizontal table of the same as the vertical ones that you're used to looking at. Then -1, 1/2. Then 0, 1. Then 1, 2. And then we will have 2, 4. And then 3, 8. Remember, the domain for this function is all real numbers. So we don't really need to, don't think that those are the only x values that we're allowed to have. Those are just, for convenience, they're easier to graph. So that's why we use those. Okay, so let's start here with the y-intercept. And then 2, 4, 3, 8, -1, 1/2, -2, 1/4. And remember how they have that smooth curve, okay? And also, we are going to have that horizontal asymptote here. Right? And for that reason, we know that for our range, it will be from, well, first I'm going to write the equation here. Horizontal asymptote. It will be y = 0. Okay. And also the range, it goes from 0, without including 0, for y value is in fact an asymptote, up to infinity. Okay, now we're going to graph g of x, which is log of x base 2. So the points we will be plotting will be 1/4, -2, 1/2, 1, -1, and then 1, 0. I'm looking at each column. Then 2, 1, 4, 2, and 8, 3. So I'm going to plot those points. Let's start with the not y-intercept, but x-intercept. No, what am I doing? X-intercept is the point 1, 0. There. And then let's go ahead and graph this one, 8, 3. We also have 4, 2. And we have, what else? Then we get the fractions, 1/2, -1. So 1/2 for x, -1 for y. And then we get 1/4, -2. So it gets closer to the y-axis. And this is how the graph will look. All right, so for this graph, we do not have a horizontal asymptote. In fact, we have a vertical asymptote. So for the logarithmic function, and you could see here, it does not touch the y-axis. So we call that vertical asymptote because it's a vertical line. It will be the line x equals 0. I know it is the y-axis, but that is where all the x's happen to be 0 on the y-axis. So let's discuss domain and range for this one. Now we already know they're inverses of each other. We even created the table in that way. So now what we're going to do is, and in fact, I want to change the color of this just because of the highlighting that I did. Okay, so in this case, we have domain was all real numbers, right? The x values highlighted in purple. So now here with the inverse function, those became the range values. All real numbers from negative infinity to positive infinity. And then here for my range values, those will be from 0 without including 0 to infinity. And so that is actually what is the domain of the logarithmic function. So just like we interchange x and y on our tables, we could also make that in a statement and extend it to the whole set of x and y's, also known as domain and range. So you could see both graphs are increasing here. And also because they are inverses of each other, they do have, they reflect across the identity function, which is the parent function, with the equation y equals x. They, if we were to fold that piece of paper, and if that was a piece of paper and we were to fold it and have along that line, you will have exactly the same thing on both sides. So another proof why logarithmic functions are important, and they're the inverse of exponentials. So we cannot know one without knowing the other. Okay, so the graphs, that is similar to what I graph. The one that we graph was base 2, you could see that. But you could have any base as long as it's, of course, not 0 and, I'm sorry, not greater than 0 and not equal to 1. So we have here, if the base is greater than 1, you will have a function that will be increasing. But if you have a base, and it's not here, so I'm just going to add it. If a is still positive, greater than 0, but less than 1, like something in the interval from 0 to 1, like any of those little fractions, then the log function will be decreasing. Okay, or it could also be like a reflection of that one across the x-axis. Okay, then also we already went over how the domain will be from 0 to x. You could also see how we have our vertical asymptote here. So x is going to get close to 0 from the right side, but it will never be 0. The range, we already know that it extends, right? It goes from the y values from negative infinity to positive infinity. And then we have the x-intercept. So the point that intersects the x-axis is at 1, 0. So we don't have a y-intercept. Instead, we have an x-intercept. And it is a one-to-one function because if we trace a horizontal line, it would only touch 1 point. You could see that. And so that tells me that it is one-to-one. Therefore, the inverse function is also a function, which is the exponential function. The natural logarithmic function, it is also a one-to-one, And we have the equation is written down here, so make sure you have that for your notes. And so just so you know why we have here two different expressions, is because first we're showing how if it says log base e, it is automatically going to be called natural log. And so that natural log, I did explain a little bit how the number e, Euler's number, it is or natural number, and that's why we refer to this as natural log. It appears in nature, it's so commonly used, and I guess that's why it has its own special name and its own abbreviation. So ln, every time you see ln, you will right away assume that it's a log base e. That's just how it works. And of course, the inverse function to the natural log function, it's going to be the exponential function. Well, let's give this one another name. If we call this g of x, the inverse function will be the exponential function e to the power x. They are both 1 to 1, so we already know at this point that they are inverses of each other. And so the way we read this expression will be the natural log of x, or ln, this is ln of x. So, and yeah, it will not have a base, but of course, when you're solving equations, you need to remember that the base is that implied e. Okay, so the natural logarithmic function, as we already mentioned, is going to be the inverse of e to the x. So here's the logarithmic function. You could see it has that x-intercept, and then here we see the exponential function e to the x is increasing, and you could see how they are both a reflection across the line y equals x, and their points are reflected across that line. In other words, they are interchanged. So if you look at the y-intercept 0, 1, the logarithmic function will have an x-intercept at 1, 0. And then also, just so you remember, the exponential function does have that horizontal asymptote that we talk about, and then the other one, the logarithmic function, does not have a horizontal asymptote, but however it does have that vertical asymptote. You can see that we're not touching the x-axis. And of course, all transformations apply to them, such as the shifting, the reflection, and all of those things. So I just want to show you quickly a few graphs where we can do some of those transformations. Okay, so I have typed some of the graphs. Here we have the parent function for natural log of x, or ln x. You could see here the x-intercept. The asymptote is not graphed for us, but we do know it's there. Then here I have an example of a vertical shift. In this case is 3 units up. So you could see how the point that used to be here at 1, 0 has been shifted 3 units up. So now you can see it up here at 1, 3. Right there. So the y value increased by 3. If we were to change that plus into a minus, you could see how the graph, then it will be shifted down instead. You could see that here, and that point that we had as reference as for the x-intercept, now we see it here at 1, -3. So that is an example of a vertical shift. And now let's go ahead and try a horizontal shift. So we have the parent function there, and here I have a horizontal shift. We have x - 2 inside the parentheses, so the graph is moving 2 units to the right. Remember, horizontal shiftings are counterintuitive. So this point from 1, 0, now it's at 3, 0. It increased by 2, the x value, plus 2. So that's a horizontal shift, and just so you know, if we change that into a plus, then it will move to the left. So the point, instead of being there at negative 1, 0 from the parent function, now we have it here at negative 1, 0. And so all the points were shifted 2 units to the left. We could also, of course, have a combination of transformations. We could have a vertical and a horizontal shift. So now what I did here with this function in green, we have 2 units to the left and 1 unit up. Okay, so just quickly, let's review the reflections. And if the negative is in front of natural log, then this is going to change all the y values. So therefore, it's going to reflect the parent function across the x-axis. And you can see that here. So, of course, with that, we could also add some transformations to it, like that, you know. It was reflected and then shifted 3 units up. So that's perfectly normal. And then we have here the other reflection. And this one, here's the parent function in red. And the one that you will see is the reflection across the y-axis. So that is also another type of transformation. So the slide that we have here with example 8 is just about how to learn how to substitute values into a logarithmic expression, in this case natural log. So make sure you do identify that key, and if it is the primary key, make sure you don't use the second function. And I think that is the case with the TI-84. The primary key is natural log, and then you see with a different color e to the x. So don't use the second function if that's the case. So in this case, the function is natural log of x. So we substitute the given values in there for x. And just make sure, as we discussed before, if you have a -1, you need to use that negative that is below number 3 on your keypad, the one that is enclosed in parentheses. And in fact, when you enter that one, you will be getting an error. And I will tell you right now why this will be, it must say error. But the reason is because the natural log, and I'll show you the graph, it is defined, the domain, it actually happens at from 0 to infinity. And so if we try to calculate the natural log of a negative number, such as -1, that is something that will be undefined. So that will be on your calculator, depending what you're using, you will get some error message. And then for natural log of 2, natural log of 0.3, and then here you have a whole expression that is irrational number. So that is very important that you enter it in parentheses, because you don't want the calculator to only calculate the natural log of 1 and then add the square root of 2 after. So if that is the x value that they want you to calculate the natural log of, make sure you use parentheses around it. And I already told you this one will be an error. Okay, so I calculated the expressions with my calculator. And so there are my answers. I will suggest that you practice how to do this with your own calculator, just so that you know that you're getting the same answers as I am. Okay, so we're almost done here, and let's review the properties that we studied previously. But in this case, it's going to be with the natural log. So you could see that for all of them, it does say ln, 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 right? So let's start from the bottom. We have the natural log one-to-one property. So if you're comparing 2 logs and saying that they are equal, is because the only reason is because the arguments are also equal. If you take the log of something that has the base that is equal to that something, such as here, the argument and the base, then the answer becomes what is the exponent right here, the x. And that is the inverse property. And they undo each other, and it works the same here because remember ln is the base e. So those when the base of the exponential and the base of the logarithm matches, then they cancel each other, and of course your answer is whatever you have left here, which is the x, the argument. Then here we have the same, almost the same, but here the exponent's a 1. Remember ln is base e, so that will cancel out, and the answer is 1, just the number 1. Then we have natural log of 1 is 0, because if we convert it to exponential, it will be e to the power 0, and any number except for 0 is equal to any number except for 0 to the power 0 is equal to 1. Okay, so that's it for those properties. They are the same. You will practice them with your homework. And here we have an example of a logarithmic function that is used to model the human memory model. So it says students participating in a psychology experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took retests to see how much of the material they remembered. The average scores for the group are given by the human memory model, and we have that listed here. F of t. T is our independent, and it is the time in months. That's important to notice because we don't know if that's in hours, in days, in years, and months. So that is the independent variable. Instead of saying f of x, we say f of t, where t is the time in months, and it goes from 0 to 12, including 0, including 12. So as an interval for that domain, we could say from 0 to 12 with brackets. And so t goes right here. And so that's the model. So it says the average scores from the group. Okay, we read that already. What was the average score on the original exam? So so we're going to see the original day. Of course, the material was newer in their head. So my guess is that they score the highest that they could. So I'm going to substitute a 0 right there. In fact, let's just do it here. Substitute with a 0. And then you could put this in your calculator, but for this one it's not necessary because 0 plus 1 is 1. And based on the rules that we've been learning, we already know that the log of 1 of any base is always equal to 0. And so in this case, 6 times 0 is 0. So the answer is 75. So the average score on the original exam, which was at t equals 0, is 75. That's the average score. Part B says, what was the average score at the end of 2 months? And so in this case, we're finding f of 2. So we substitute the 2 in place of the x. And for that one, I am actually going to put it in the calculator. And then for the next one, which is what will be the average score by t equals 6. So in that case, we were going to substitute t with a 6. That will be 6 months after they took the exam. And Actually, I made a mistake here. This should say 6. Okay, so I'm going to pause the video and calculate this. Okay, so I calculated what will be the average score at the end of 2 months. So I substituted x with a 2, and the average score I got was 68.41. And then for after 6 months, I substituted x with a 6. You could type the whole thing on your calculator at once. Here, this number 6 is multiplying, so you don't even need to put a symbol in between. The calculator will read it as multiplication, and then the average score after 6 months, I got 63.32. And just make sure that you are pressing the correct key, the one that says LN for natural log. So this is the end of the video.